So for 7.3, what we're going to do is talk about sample means. So it's going to be very similar to what we talked about yesterday. It's going to be talking about means, but instead of talking about portions, but now averages. Right? So you're going to see a lot of similarities and differences between what we have talked about in 7.2 and what we're talking about. First thing I want to talk about is the sampling distribution of X bar. Right? So suppose that we have an X bar, and you guys should remember that X bar is what? What's that the notation for? That's a sample mean, right? So this is going to be a sample mean. So suppose that the sample mean is the mean of a simple random sample of size n drawn from a large population with a mu. What does mu represent? Population. So that's going to be a population mean. And a standard deviation sigma. Now, would you say sigma is a population standard deviation or a sample standard deviation? And why would you say population, Madison? Because it is a Greek letter, so usually our population parameters are in terms of that. So, okay, you guys with me there? All right, let's continue. So if this is true, then the mean of the sampling distribution of X bar is going to be mu sub X bar equaling mu. All right, so that means that the mean of the sampling distribution of X bar is mu sub X bar, which is equal to mu. So notice here that the mean of all the sample means is equal to the true means. If you've been paying attention this week, we also describe this in a certain way. How else could we describe this? What could we call mu sub X bar if it equals mu? Say that louder, Courtney. Unbiased. It's unbiased, and what do we call it after that? Unbiased estimator. All right, so we talked about that in 7.1. So if the mean of all the sample means is equal to the true mean, then we have an unbiased estimator. You guys good there? Excellent. So then for the standard deviation of the sampling distribution of X bar, we have sigma sub X bar, and that's going to be equal to sigma over the square root of n. All right, you guys probably remember that from the Party Sabetti video. Remember she told you about that? The relationship between the population standard deviation and the sample size. So sigma sub X bar is equal to sigma over the square root of n. All right, here we talked about this idea a little bit yesterday. Can anyone talk about what we discussed when we had said that big N was greater than or equal to 10 times little n? What did that talk about? Start with an I. Independence, right? And remember here that we're talking about a very large population, correct? And not every observation within a set of data, whether it be a sample or a population, is going to be independent. But if we're talking about a very large sample from a very large population, over time, the differences between those values are going to be kind of negligible. All right. So even if we do have dependent scenarios, we can kind of almost assume independence if our population and our sample size are higher. Does that make sense? We've talked about doing that. Do you guys remember the proportion I put on the board yesterday? And we said that those proportions were pretty much equal. You don't remember that, do you? Like we talked about 2,468 over, I don't know, 3,172. And we were saying, is that equal to 2,467 over 3,171? Are these technically equal? No. No. But are they close enough? Yeah. Do you guys remember us doing that now? No, I wrote it on the board. So then we could kind of say, okay, we're going to assume this is true. All right. And we're going to talk more about independence when we get into confidence intervals and hypothesis testing. All right. But as long as your sample size and your population size are large enough, you should be okay to assume independence. You guys good there? Mm-hmm. All right. So that's a basic introduction to the sampling distribution of X bar. All right. So checking for normality. We're going to do 3 things here to check for the normality. First, if the population distribution is normal, then the sampling distribution of X bar will also be normal. That should make a lot of intuitive sense. If the population's normal, samples you take from the population should also be Normal. You guys understand? Like, that makes a lot of inherent sense. And that means that here, this is true no matter the sample size. Like, sample size we do not care about here because our data come from a normally distributed parent function or parent distribution. So that means that our sampling distribution of x bar will be approximately normal regardless of sample size. All right, so those data are normal from the parent. The sampling data should also be normal. So the second part here, if the population distribution is not normal, then we use our friend that we celebrated. You guys remember a big celebration of the central limit theorem? And I gave you cupcakes, and I said, Happy Central Limit Theorem Day! And you guys were scared, and JT wished me happy birthday, but it wasn't my birthday, and which was nice. I wish it was my birthday. I wish someone celebrated me as much as we celebrated the central limit theorem. I know. It just so happens to fall over break. But anyways, remember our central limit theorem tells us that the sampling distribution of x bar will be approximately normal in most cases if we have our unwritten rule here. Do you guys see our unwritten rule? Yeah. Of n equals 30 or greater than 30. Remember when we watched the Party Spaghetti video, it was if your n is large, like, well, how large is large? So we have this kind of unwritten rule here that it's going to be anything over 30. Okay. Now, it needs to be noted here that the population distribution will not become normal. What are we commenting on the normality of? We're not commenting on the normality of the population. What are we commenting on the normality of? The sampling distribution of x bar, right? Of the means. This is what we're talking about, is being approximately normal. Does that make sense? So you need to understand that the population distribution, unless it is already normal, will never become normal with sampling. Only the sampling distribution will. All right, and our third case, let's say we have less than 30 in our sample. Let's say we have less than 30. What we'll need to do is we'll need to graph our data, and we need to assess normality from that visual graph. So if we talk about graphing a data set from something that has a sample size of less than 30, what are we looking for to say, hey, this could be approximately normal? What kind of shape are we looking for? We're looking for bell-shaped, right? And we're looking for what? Say it louder. Say it with pride. Symmetric. Say it so the YouTubers can hear you too. Right? Okay. So what else? Unimodal. Very nice there. Unimodal. So that means if our sample data, let's say, looks like that. Let's just say that this is n equals 28. I'm making this up, guys. Let's say n equals 28, and we have a histogram that looks like that. Now, this is a rough-looking histogram, but do you guys get the idea here? Would you be able to say that's approximately normal if your histogram looked like this from your samples? This is not approximately normal to you. I would say this would be okay. Remember, we're talking about rough here, right? I mean, is it skewed in a direction? No. I mean, is it single peaked? Is it pretty symmetric? I mean, this would be like a rough. Oh, sorry, you guys don't spell rough that way. You spell it like this, right?
It spells it like that. No. It's always spelled tough, not rough.
You spell tough with 2 F's?
Sometimes.
That doesn't make me feel like you're really tough if you're spelling it with 2 F's, right?
It doesn't add tough, like you failed your stats test. Oh, that's tough.
Is that like a slang word that I don't know of?
You already heard the outsiders. Things are not a lot. Top.
Listen, the more you know. The more you know.
That's
All right.
friends.
The more you know?
Yeah.
Yeah.
That, I don't know.
Or it can be rough.
That doesn't sound like heavens to Betsy. Like it doesn't. All right. But anyways,
That's happens to Betsy.
yeah.
Embrace it.
Yeah. Okay. All right. Do you guys remember us talking about the new z-score yesterday?
Yeah.
Okay. So I'm going to write the old z-score up here. And that old z-score is not going anywhere, but we're going to amend it a little bit for sampling distributions, right? So this was the old z-score. So the new z-score, now I also gave you a formula sheet yesterday. You guys remember that formula sheet? On the back it said that this thing here was the statistic. Now, in our old z-score, that is not a statistic. That's just a single observation, right? It's a single observation. Our z-score now is not going to be talking about a single observation. It's going to be talking about the average of like 20 observations or like 70 observations instead of just a single operation. So here, we're going to replace this with the statistic. So if we're talking about sample means, what's the little symbol for sample means again? X bar. What's going to be our statistic here? So instead of X, I'm going to write X bar. So X is going to be replaced with X bar. Subtract. This mu should be our parameter. What's our parameter here going to be for X bar? What's the symbol for a, not a sample mean, but a population mean? Not P. P is for proportion. What's the population mean symbol? Mu. So does it change? No. Isn't that nice? Just copies over. Divide by. Then right here, remember this bottom part is the standard deviation. This would be our standard deviation of the statistic. Now, earlier today, we talked about what that looks like. So sigma is going to morph a little bit. What's sigma going to morph into? Sigma divided by square root of n. So let's talk about some similarities and differences between our old z-score and our new one evolving sample means. What's the similarity here? Mu. That just copies over, correct? What's the difference?
Standard deviation is divided by
The square root of,
the same.
instead of just being normal sigma, right? And x becomes X bar. So when do you use which? This first one is going to be when you have n equals 1. So it'll say like a randomly selected patient or something like that. Let's just say like a randomly selected patient. Notice that's a single thing. Like what's the probability that a randomly selected patient has more than 1, right? This new one here is going to be, what's the probability that 40 randomly selected patients have blah, blah, blah. So when am I going to use old versus new? When I'm talking about a single randomly selected patient versus 40 randomly selected patients. Does that make sense? You'll have a number that goes along with it. All right, like 40, 20, 70, 144. Spoiler alert, that's going to be an example later. All right, is that good? All right, moving forward. All right, what are some behavior patterns of sample means? What are some of the behavior patterns? Well, first, the sample mean is an unbiased estimator of the population mean. And if that's true, then that makes sense that mu sub x bar should be equal to, good, mu. Thanks, class. Excellent. Katie?
Is the blank on the bottom of the paper flashy?
from the last screen. Used when there are samples of size n. You'll have some random sample size that you'll have to deal with. And it'll be worded similar to this little star bullet point. Okay. All right. Values of x bar are less spread out for larger samples. The values of x bar are less spread out for larger samples. And that goes with the next thing, because that means that the sampling distribution will be less variable than the parent distribution. This goes back to the whole idea that as n goes up, sigma sub x bar should go down. As you increase sample size, you decrease variability. And that's definitely true in comparison to talking about sigma versus sigma sub x bar. Do you guys know the differences and the similarities between sigma and sigma sub x bar? Some of you guys are saying no. This is the population standard deviation, right? This is the standard deviation. Sorry, like that. This is going to be the standard deviation of x bar. For the sampling distribution. This is the standard deviation of your sample means. So like you have a bunch of sample means, right? Graph. Sigma sub x bar measures basically the spread of that. It's basically the spread of all your x bars. Yes?
Yes.
Yes, cool. All right, cool. Moving forward. All right. The next two bullet points here, we're going to discuss in example 1. So if you do not fully understand them, we're going to see these in action in example 1. The standard deviation of the sample mean decreases at a rate of the square root of n. And well, this is actually seen because if you're talking about this sigma sub x bar, that is sigma divided by the square root of n. So it's basically dividing in the square root of n into sigma. So it's decreasing over time. So that's why sigma sub x bar will always be less than sigma. All right? It's going to be a smaller number as n goes up. You're going to see a little pattern that happens here. So you can go ahead and write this down. Some students understand this, some students don't, and that's okay because you can do this algebraically regardless if you understand this. All right? But this means that you must take a sample 4 times as large to cut the standard deviation in half. So if you want to cut your standard deviation in half, you take 4 times the sample size. And we're going to illustrate that here in just a moment. All right? You guys with me? If you don't understand that in a minute, I will show you via an example. All right. So let's go ahead and do that. Well, after we do the describing the sample mean distribution. Recall that we use the center, the shape, and the spread to describe any quantitative distribution. This is also known as SOX, right? So how would I discuss the shape here? What's the shape of a sampling distribution if n is high? Approximately normal. You guys got to know that. So sampling distributions are approximately normal if your sample size is large enough. And this is a big bullet point again. This is because of the central limit theorem, and that's regardless of the population distribution. So as long as your sample size is high enough, your sampling distribution will take an approximately normal shape. So how should you describe the quote-unquote shape of a sampling distribution? You basically say it's approximately normal. And that will be true as long as n is large, or if your population is normal. You guys follow me? The center is given by the mean sub x. So the mean of all your x bars is going to be equal to mu. So when you're asking, how do I describe the center? You're going to literally report the mean measurement. That's the center. For the spread, you're going to describe it by sigma sub x bar, which is equal to sigma over square root n. So if they ask you, how do you describe the sample mean distribution? What you're going to do is what? Say it louder.
Socks.
Say it for the YouTubers. Say it for your classmates.
Socks.
Socks. There you go. Thank you. Nice. Disclaimer, YouTubes, it's fourth period on Friday. They're really quiet on Friday afternoon. They're asleep. It's nap time. Anywho, we're going to do some examples now from all of this, right? So hopefully you guys are ready for examples. We'll move out of the way. Yes, sir. All right. So now move out of the way. No yawning at fourth period. That's cheating. All right. It's not really cheating, though. Maybe if I was a little bit more entertaining. It's not even that. Just tired. Everyone's tired. You know who's not tired? Me. All right, example 1. Suppose that sigma sub x bar is equal to sigma over the square root of n. Hey, we know that, right? Things to note for this chapter. That thing. It's on your formula sheet, too. You guys find it on the bright orange formula sheet that you have?
Somewhere.
Yeah, I gave that to them yesterday. Yeah, you guys don't get one. Yeah.
You guys get
That's what happens when you go to track meets. You don't get one. All right. So sigma is going to be 16 and n is going to be 25. Can you find x bar, or sigma sub x bar, excuse me. Can you find sigma sub x bar?
Yes.
Yes, how are we going to find that? Plug it into the formula. Yeah, that's going to be 16 over the square root of 25, right?
no beating people up there.
All right, so what's the square root of 25?
5.
5. So that's going to be approximately what? 3.2. You guys good with that? So what is the standard deviation of our sampling distribution of x bar? 3.2 or 16.5, whatever you guys want to do. All right. So I'm going to erase that because when I click the next screen, I'll rewrite this to 3.2. What would you use as your sample size, or what would your sample size need to be to reduce sigma sub x bar to 1/4 of the value that you found in part A? So what would your new sample size need to be to shrink the standard deviation of x bar by 1/4? 8 times larger. So you can literally do n equals 25 times that by 8, and you're going to get what? 200. Do you guys want to see how that really works? Why is this true? Well, think about this. Well, sigma sub x bar from the original should be what? 3.2. You want to cut that in 1/4. You want to take 1/4 of that. So what's my new one? Don't all help me at once. 3.2 divide by 4. 0.8, right? You guys agree? All right. So let's see. So that's going to be sigma sub x bar is now going to be 0.8. So 0.8. Now that's going to be equal to what? 16.
Over 20.
Let's make these the same color, shall we? Multiply both sides by the square root of n. Divide by what? So that'd be the square root of n is equal to what? You guys have the calculator. I have no calculator. 20. So what should I do here to get rid of that? So actually, it's not actually 200. It's what? 400. Where did we go wrong up here? You did 4 times 2 to get 8, right? But it should have been what? 4 times 4, right? Which would be what? 400. So every time you want to cut the standard deviation in half, you have to times it by 4. So you times it by 4, but then double that. You guys see that's not timesing by 4 twice?
Yeah.
So instead of doing 4 times 2, you could have done what? 4 squared. So I'll let you guys make that mistake to illustrate that. Because if you don't understand that, because you think you're going to remember that in probably a week or 2, let's be real, no. But can you always solve this? Yeah, you can. You have the skills now. In your mathematical, awesomeness, how savant you are. Yeah, just throwing out the English vocabulary.
Word of the day.
Word of the day, right? Folly? It's a silly word.
I wrote about statistics for my word of the day.
Uh-oh.
I said AP statistics is going to be my folly as a high school senior.
Is it really?
It's my worst class.
Is it your hardest class?
Yes.
Well, we're working on it, right?
Well, when I'm doing homework, I feel like it's fine, but when I get to test,
I'm sorry.
it's my fault, I guess. So it's like whatever. It's like who even cares?
All right.
Okay,
You guys ready to do this example? Example 2?
Yeah.
There were 5,317 previously owned homes sold in a western city in the year 2000. The distribution of sales prices of these homes was strongly skewed to the right, with a mean of $206,274 and a standard deviation of $37,881. If all possible simple random samples of size 100 are drawn from the population and the mean is computed for each of these samples, describe the sampling distribution of the sample mean sale prices of the homes sold in this western city. Okay, what are we asked to do here? Boil this back down. What is our goal? We want to describe the sampling distribution of the sample mean. So we want to SOX up what? X bar. We're SOXing for X bar. So we got to do a couple things, correct? How do we SOX X bar? Number 1, we need to talk about the shape. Anyone pick up the parent population shape? Not just skew to the right. All right. Does that mean that the shape of the sampling distribution is strongly skewed to the right? No. What is this based off of, the shape? The sample size, right? Very good, Maria. It's based off the sample size. So what's our sample size here? Random samples of size what? And you're taking all possible simple random samples, correct? So you're taking a lot of samples. So what do we know about the shape here? It's going to be approximately normal via the central limit here, right? Because n here is going to be equal to 100 in this case. All right, sorry, n is going to be equal to 100 in this case. So if we're taking all possible simple random samples of size 100, that means that this is a sampling distribution. It's a true sampling distribution. Not an approximate sampling distribution, because you're actually accounting for every single possible simple random sample, right? You're accounting for all combinations of 100 out of 5,317 things. That's a lot of sample means. So this is the almost perfect sampling distribution here. So that's going to be approximately normal. You guys good with that? Center. That's going to be the mean of X bar should be equal to what? The means of X bar? What is this equal to? The population mean. And what's the population mean? 206,274. 206,274. All right. Spread. how do I calculate the spread here? You're not going to say high variation. You're not going to say low variation. You're going to give a specific number. And how do we calculate said specific number? We need to find the sigma sub x bar. So remember, that's going to be sigma over the square root of n. You guys with me? Sigma over square root n? So that's going to be, what, 37,881 over the square root of 100? Which is going to be 37,881 over 10, which is going to be what?
3,788.
3788.1, so $3,788.01. Now, you guys do realize that this is an outline.
Yeah.
Okay? We need to make one statement. Now, you could write this in one sentence to answer this question. You guys with me there? Good. So, remember these things, because we're now going to erase this. And I need to show you what you need to write in order to get full credit for this. All right, so what are we going to say? We're going to say first the sampling distribution of what?
Previously
Of the sample mean.
Sales prices sold in the Western.
Of sales prices of the homes sold solid. Oops. In this western city is what? Shape. Approximately normal. I'm going to put in parentheses due to large sample size. With mean of what? 206,274 and standard deviation of what? 3,788.1. 10. Same thing. All right, you guys good? What you need to write there? Yes, no? Excellent. You guys ready to do the final example of the day?
Yes.
Awesome. All right, example 3. A recent study was conducted to investigate the duration required to complete a certain manual dexterity task. The reported mean was 10.2 seconds with a standard deviation of 16.0 seconds. Suppose that the reported mean and standard deviation are the true mean and standard deviation for the population of subjects within the study. If a random sample of 144 subjects is selected from a population, what is the approximate probability that the mean of the sample will be more than 11 seconds? All right, we got a lot of stuff to organize here, right? So guess what we're going to start with? Organizing your info. With sample means, you generally get a X bar, right? Along with a population mean. Along with a standard deviation. Along with a sample size. Do you guys see you have a lot of numbers up there? There's actually 1, 2, 3, 4. And notice that I've written out 4 things for you. Can anyone identify one of these 4? X bar, mu, sigma, or n?
N is 144.
N is 144.
Standard deviation is 16.
Standard deviation 16.
X bar is 11.
X bar is 11.
Mu is 10.2.
And the mean is 10.2. Now, why do you know that the mean is 10.2 and not 11 for mu?
The true
Because it says the reported mean was 10.2 seconds, and then it said down here that the reported mean is the true mean, right? And that the reported standard deviation is the true standard deviation. You guys with me? All right, cool. What are we trying to find here? The probability of what? What is the approximate probability that the mean of the sample will be more than 11 seconds? So in probability notation, what are we trying to find? P parentheses of X bar being greater than 11.0 seconds. So that's what we want to find. All right, that's what we're interested in. All right, in order to calculate that probability, we need to assess the normality situation. So I have a question. Is the population normal? Did it say the population distribution of this is normal, skewed left, skewed right? Do we know? Next. Do we know our sample size and see if that's greater than or equal to 30? It is greater than or equal to 30. So then here we can say that the sampling distribution which means not the population, the sampling distribution of X bar is approximately normal via the central limit theorem. Okay? So our sampling distribution of X bar is approximately normal via the central limit theorem. Because if our sample size is high, then the sampling distribution of X bar will be approximately normal. That's good there? So now, what does that give us the ability to do? Normal CDF, inverse norm, all those cool things in our calculator to be able to calculate probabilities on the normal curve, right? Okay, so we had to at least check that normality thing. All right, what are we doing for number 3? Let's organize mu sub x and sigma sub x bar, right? Now, what is mu sub x going to be equal to? Mu, which is going to be 10.2. Sigma sub x bar is sigma over square root n, right? And that's going to be 16 divided by the square root of, what, 144? And what's that going to give us? 16 over, well, square root of 144 is 12, right? Which is 4/3. 1 1/3. Got to do that quick math, mental math, right? So you have all that, correct? So now we're going to go to step what? 4, and we're going to finally calculate the z-score, right? So 4, we have our new z-score formula, right? That's x bar minus the mean over sigma divided by the square root of n. You guys remember that from our earlier talks?
Yes.
So you guys told me that x bar was 10 point... No, that's not 10.2. Which one's the x bar? 11. We should take away 10.2 and divide that by 4 over 30, or 4 over 3, 4/3. All right, so what's my z-score here? 11 minus 10.2 divided by 4/3? So that's what, 0.8 divided by 4/3, so that's what? 4/5 divided by 4/3, so that's 3/5, so that's 0.6, or 3 over 5. I was doing it in my head. Give me a second.
Draw a picture.
For what? What picture are we drawing, Taylor?
The z-score.
I would like the YouTube generation to know that the class has to draw this because they did a boo-boo on their test. And they did not label things as their AP reader teacher told them to label. So now they have to do all the steps until further notice, or Mr. Bird will take off. They did this to themselves. Anyways, that was like a sidebar in theater, right? It's like a sidebar. It's like when you face the audience and you start talking. That's what I was doing. Okay, whatever. You knew what I meant. Jeez. Ugh. All right, 0.6 is a little bit over, right? So So z is equal to 0.6. We're going to shade which direction?
Right.
To the right. All right, so go ahead and calculate that using your calculator, but not writing the words normal CDF on your paper. Bless you, Katie.
Thank you.
You're welcome. I should have played the Jeopardy music. Courtney? Point 0.2743. All right, ladies and gentlemen, what does this mean?
There is a 27.4% chance of the mean of the sample being more than 11 seconds.
There is a 27.43% chance that the mean of the sample will be more than 11.0 seconds. All right. That will be the end of our notes over 7.3 for today. Do note that there is an AP free response on the other side of your paper. We will do that when we review Chapter 7 and Chapter 8 on Monday. You guys good? Any final words for your comrades, friends, classmates who are not here today? You want to give them a shout out? You want to say hi?
Don't forget to leave a like and subscribe and hit that bell icon to get notifications every time we upload a new video, and hit the link in the description box down below to win a free MacBook and use promo code for its AP Stats class to get your first audiobook on Audible for free.
Yeah, you should do that. Definitely do that. All right.